Only valid at equilibrium because now I'm putting it in to this equation for the equilibrium constant. So here the T naughts over T's cancel. Concentration terms cancel. And we simply get that pretty nice equation at the end. Equilibrium conversion divided by 1 minus the equilibrium conversion. Okay, so that's equation 1. And here is equation 2. Right? Wow. So we'll write that one out again in a slightly neater way. We're just going to get rid of that log term. So this is what they use in the book, and they've got one of these for equilibrium constants, and they also have one for rate constants. And this is where I think some of the nomenclature can get confusing, so we'll make sure it's clear. And so again, this is assuming, well, this is delta is equal to 0 or very small, right? The term we had up there had a delta. Here it's just equal to 0. It's also assuming that delta H reaction is constant over what temperature range? We don't have a T2 anymore, right? So this is where I mean some of the nomenclature can get confusing. What temperature is T0?
T1.
T0, this one right here. The inlet, right. So I have PFR, and sometimes we even had multiple ones, so we would call this one PFR1, T0. What's coming out?
T.
T. What if I had multiple reactors in series? What would we have called that?
T1.
T1. Is that what this temperature is? No. This is the temperature, because you're going to be given an equilibrium constant. So remember how we were given a rate constant in the last problem at 300 Kelvin? This is that temperature if you were given, and we're going to do an example in a second. This is not the temperature coming out of the reactor. That is just T. So this is just T, then T1, and so why did they use 1? Why didn't they use like reference since you're given a reference? Well, we already used that for delta H of reaction. So there's a lot of temperatures now that you have to keep straight. If you want, you can think of this as like TG, temperature given, or something like that, but that's what it is. It's the temperature for the equilibrium constant that you're given. And then sometimes there's a very similar formula for a rate constant. Sometimes you're going to be given an equilibrium constant and given a rate constant, and those temperatures aren't going to be the same. So just don't let it confuse you. And like I said, this is where in the book, he does everything. He just, T1, T2, T3, he just keeps going as if there's no issue with that. Okay. But yeah, it can be confusing if you're talking about multiple reactors, because you might want to say that T1 is the temperature leaving reactor 1, just like we said X1 was the conversion leaving reactor 1, and so on and so forth. So, an example might help. Well, we'll put up an example just in a second here. All right, so what do you get from this equation We talked about this just a little bit. If this is for exothermic, and this is endothermic, what's the shape of this curve going to look like? So as I increase temperature for an exothermic reaction, does the equilibrium conversion increase or decrease? Decreases. So we have two data points. Is that going to be a straight line or some curve? Do we know the shape of that curve at all? So yeah, you guys might not know it off the top of your head, but it's not linear, right? You at least know it's not linear, I hope. Because there's a formula right there. It looks kind of like this. And then this one's going to look like what? Just the opposite, right? All right, so now let's look at an example. And then we'll be done for today. Okay, normal butane is being reacted with isobutane in a liquid reactor. It's a reversible reaction. It's going on in a PFR. The delta H of reaction for this minus 6.9 kilojoules per mole. The initial concentration of N-butane, 9.3 kilomoles per meter cubed. The initial flow rate of N-butane, initial flow rate of product is 0, and the problem statement actually says that the feed is 90% N-butane and 10% pentane. So we're going to treat pentane as an inert. So what is this theta I equal to?
98.
1 over 9. 10% pentane, 90%, sorry. Yeah, 10% pentane, 90% N-butane. So it's 1 over 9. No, just 1 over 9. It's just the flow rate divided by the flow rate. We're given some more stuff. 65.7. So both the butanes have the same heat capacity. So the delta Cp of reaction is just 0. And you're given the heat capacity of, I guess this is isobutane technically, is 141. But remember, that would be the same as the heat capacity of N-butane. And notice that I didn't, so this problem is actually a little bit different than the textbook. Here I'm giving you the pre-exponential factor. In the textbook, what it does is it tells you a rate constant at a particular temperature. That's why, I mean, it can get confusing because you're going to be given an equilibrium constant at a temperature, you're going to be given a rate constant at a temperature, and you got to deal with the reference temperature for the delta H of reaction, you got to deal with the inlet temperature going into the reactor, and the outlet temperature. There's about 5 different temperatures that you have to worry about. Don't let it confuse you. Okay. So, design equation. So that's the design equation for PFR. What is the rate equation? We're going to assume that it's an elementary reaction.
If you tell us it's an elementary reaction, but there's a 2 at the front, do you still move it to the right side?
No. So we'll talk about this when we go over the test, but guys, you never truly move that stuff over. If you look in the textbook where he's got his stoichiometric tables, they all say B over A. A is still A. You haven't actually made 2 a 1. All you've done is said, okay, now I'm going to, in my stoichiometric tables, I'm going to use B over A instead of just B. That's the only place that division happens is inside your stoichiometry table.